Right, carrying on with the 2023 Oxford PAT, we got to question 19. Solve the following equation for real x. So let's just do a little substitution then and say, y is equal to e to the x. So we've got 6y squared plus y equals 15. Well, let's just write it as minus 15 equals 0. Is that going to factorize? So we want two numbers that multiply up to minus 90 and add up to 1. So yes, it will do then. So we'll have 6y squared plus 10y minus 9y minus 15 is 0, splitting that middle term. So we'll have 2y, 3y plus 5 minus 3 lots of 3y plus 5 equals 0. So that's 2y minus 3, 3y plus 5 equals 0. So that we've got y is equal to 3 over 2 or minus 5 over 3. So that means e to the x equals 3 over 2 or minus 5 over 3. Well, e to the x is not going to be equal to minus 5 over 3. So we need e to the x is equal to 3 over 2. So we've got x is the natural log of 3 over 2. So we just got the one solution there. Right, that was easy for 3 marks. That's just a standard opener question for an A-level paper. Question 20. A diver 5 meters under the surface of the sea looks up. They see a circle of light directly above them where they can see what is on the surface, but outside this circle they see only a reflection of what's under the water. Explain why there is such a circle and calculate its radius. Right, a little picture isn't going to go amiss on this then. So if that's the surface and you've got the diver down here at this depth of 5 meters, then what's going to happen is you're going to get some critical ray, aren't you, where you're going to get total internal reflection at the surface. That's where we've got our critical angle going on there, same on the other side. So you're going to want to say that that at some point, how have they phrased this? See a circle of light directly above them. So you can say something like the angle of incidence of a light ray from the diver to the edge of the circle, is the critical angle, is theta c. You want to say that it's the critical angle. So beyond this angle, therefore beyond this angle, there's total internal reflection. So you're measuring all, you're mentioning all of the key things. Obviously, write out total internal reflection rather than doing TIR. Actually, write out the words. But you want to mention, the key scientific terms in all of this. So that's what's going on there. And we have to calculate what that radius is then. And they've given us n air and n water. So we've got then that if we're working that out, we're going to get 1.33 sine theta c. This is our critical angle, is going to be equal to 1. So that is going to be theta c as well, isn't it? So we can, if that's the radius, that's theta c. So tan of theta c is going to be opposite over adjacent, which is r over 5. So we just need to plug all of this in and get the, we're working out r, aren't we? So r is equal to 5 tan theta c, and theta c is sine to the minus 1 of 1 over 1.33. So if we plug all of that in, we get that r is 5.70210321. So 5.7 meters. That's a nice question. I like that. Something a bit different. It's relatively easy to do the calculation, but conceptually you have to get inside it. Question 21. Find all values of x that satisfy that equation. Oh, yawn. Right, well, we're going to want to get rid of the cos squared bit here, get everything in a quadratic in sine. I mean, talk about lack of imagination putting in a question like this. So we've got 4 sine x sine x, and then cos x is 1 minus sine squared. So we've got 1 minus sine squared x is equal to 3 plus sine x. So we've got 4 sine squared x plus 4 sine x and minus 4 sine cubed x is equal to 3 plus sine x. So we can take the sine x off of each side, and oh, actually the sine cubed is negative, so let's put everything on the right in inverted commas. So 4 sine cubed x minus 4 sine squared x minus 3 sine x plus 3 is equal to 0. Have we got all those 4s and 3s look nice? So 4 minus 3 plus 3. So we've got a sine x minus 1 is going to work as a factor. So we must have a minus 3 there, 4 sine squared x there. So how many? Oh, we don't need anything in between because that gives us what we need. So that's difference of two squares. So we've now got sine x minus 1. Oops. Minus 1. And then it would be 2 sine x minus root 3, 2 sine x plus root 3 equals 0. So all in all in this, we've got the, let's scroll down a bit. So we want all values, so I haven't even limited any kind of range on this. So for sine, we got sine x equals 1 is one bit. So we're going to have, that's going to be at pi by 2 and then every 2 pi. So that's what we get on that. So that's for n is integer, because we'll use that n all the way through. Then we're going to have that sine x equals root 3 over 2. So that is 60 degrees, so pi over 3. And then we're going to be adding on 2n pi, but we're going to have another solution, aren't we? Because we're going to have it's going to be pi minus pi by 3. So it's going to be 2 pi by 3 plus 2n pi. Then we've got that sine x is, what's our last one? Minus root 3 over 2. So that means we're going to have, well, we're just going to have the negatives of these. So minus pi by 3 plus 2n pi and minus 2 pi by 3 plus 2n pi. Boring, 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 but there you go. They're giving you 5 marks to do that. But yeah, totally useless. Right, question 22. 2 identical spacecraft of mass m are in stable circular orbits around the Earth, one at height RE, the other at height 2RE. Assuming that's the radius of the Earth, is it? Yes, it's the radius of the Earth. What is the difference in the total energy of the 2 spacecraft? Right, so we've got one, they're both m, they said, right? So we've got one of them at an orbit of 2RE, because it's got a height of RE above the radius of RE, and then we've got the other one which is at 3RE, and they're both mass m. So the one that is at the greater orbit, so this is going to have a higher potential energy and a lower kinetic energy. That's what we're going to have on that. So, because we're not magicking up energy from somewhere, so they're going to have, you know, similar. This is the thing: as you get closer in, you're losing the potential energy, and you've got a higher kinetic energy. I mean, you can see it in Kepler's third law as well, can't you? You have to be moving slower in order to sweep out the same areas in the same sort of time. So, let's start then with the kinetic energy. So we're going to have, how are we going to do all of this? So we're doing stable circular orbits, right? That certainly helps, because I was wondering where we were going to go with all of this. So we need GMM over R squared. Let's put this in inverted commas. So that's our force due to gravity. That's going to be mv squared over R, because we're in circular motion. So we're going to have that a half mv squared, that's our kinetic energy, kinetic energy equals a half mv squared, which is going to be equal to gmm over 2r. So that's what we've got there. So the difference in the kinetic energy is going to be equal to gmm, because we've got the higher kinetic energy here. So higher kinetic energy for the smaller one. So I mean, you can see that in this formula now, can't you? That we've got, as you increase r, the kinetic energy drops. So we've got, that's going to be over 4re then, and then we can take off gmm over 6re. So a quarter minus a sixth is a 12th, isn't it? Yeah, because that's going to be 3/12 minus 2/12. So that is equal to a 12th. So gmm over 12re. Okay. So now we need to do for the potential energy. I mean, you can do this in, I suppose you can do it in a number of different ways with this. You can either just know the potential energy formula for this, but what we're really doing is we're integrating from 2re to 3re. We're saying as we're going from low to high, we're integrating the force over distance. So our gmm over r squared over the distance, that is going to be the change in the potential energy. That's the work done as we move along this potential gradient. So yes, this is why we're going to get a 1 over r thing going on, So we're going to get minus gmm, and then that's going to be a 1 over r from 3re. I haven't dropped off the side of the screen, I don't think. So that gives minus gmm, a third minus a half. So a third minus a half is minus a sixth. So yeah, we'll have minus a sixth there. Oh, I've got an RE as well, no, RE. So let's scroll down and put all of these things together then. So the total difference that we've got, how have they phrased it? The difference in total energy. Okay, so let's actually write that out then. Difference in total energy is going to be equal to, so here we've got gmm over 6re. So that was the gain in energy moving from the 2re orbit to the 3re orbit. So if we take off the difference in the kinetic energy, because it's higher in the 2re orbit, but this is the higher in 3re, so we need to take off the higher in 2re. So we've got gmm over 12re, and that's going to be, well, it's going to be gmm over 12re. So yeah, that's right. That's a step up in difficulty there for 6 marks. I mean, it is, again, it's not crazily difficult, but that's not too bad. You don't necessarily have to do the integral here. I mean, if you know how the potential is changing, you can just go straight into talking about gravitational potential, saying it is, minus gm over r. So of course you have to then multiply by the new m, and that's going to give you that potential. So that's, energy. This is the energy per unit mass, isn't it, for gravitational potential energy? So if that's energy per unit mass, multiply it by the mass, and then you've got the potential energy. So that's how we're getting our GPE. So you could just jump straight into that, but it's no hardship doing that integral. Plus it shows, I suppose, that you know the relationship between the force and the energy there by, where does that equation come from? So yeah, that was a nice question, question 22. I think that's probably been the toughest one so far. And try and squeeze one more in. I think this hasn't gone on too long, so let's do question 23. Oh, we got another optics question. A beam of light, excuse me, in a medium with refractive index n1. Oh, okay, so that's that picture. And n2 is greater than n1. The rear surface of the slab is mirrored and perfectly reflective. Okay, I assume they're going to ask us a question somewhere. What distance L does the beam transmitted into the slab travel before re-emerging from it? Express it in terms of M1, M2, theta 1 and D. Right. So we've got this distance L. So N2 is greater than N1, so it's going to refract towards the normal. Then you get perfect reflection, and then it's going to refract back out again away from the normal. So we can say that there, well, L is, what did they say? L is the total distance. What was it? The total distance L traveled in the slab. Right, so each one of these paths then is going to be L over 2 each way. So let's zoom in on the boundary here. We've got that, then we've got that. That's our theta 2, although we can't use that in our answer. That's our theta 1. That is L over 2. That is then D for where we hit the wall to there. So we've got that, what have we got? We've got a cos theta going on here then, haven't we? So we've got the L over 2 cos theta 2 is equal to D. And we've got our usual N1 sine theta 1 is equal to N2 sine theta 2. So we need to get rid of one for the other. So we want L. I can scroll down again. We want L. So L is 2D divided by cos theta 2. And then from here we can say that sine theta 2 is N1 over N2 sine theta 1. So that is going to be 2D over the square root of 1 minus sine squared theta 2, just using our trig identity. So we just need to put it all in now, don't we? So we've got 2D over the square root of 1 minus N1 squared over N2 squared sine squared theta 1. Which I think is L, so they were allowing us D theta 1 N1 N2, D theta 1 N1 N2, right, so no problems there. So that's good. What are the limiting values of L at large and small theta 1? Right, so that should, and they get 3 marks for this second bit. It's a bit weird, isn't it? So limiting values of L, so for small theta 1, i.e. Theta 1 is equal to 0, we're going to get L is equal to 2D. So yeah, that's going to be, well, L min, maybe call it L min is equal to 2D, which makes sense. You've just gone straight in, bounced out again. There's been no refraction at the boundary. You've arrived normal at the interface. So for large theta 1, so i.e. we're going to have that theta 1 is nearly equal to pi by 2, then we're going to get, well, sine squared theta 1 is going to turn to 1. So we're going to have L is equal to 2D over the square root of 1 minus M1 squared over N2 squared. So good. Yeah, it was an easy 3 marks compared to the first bit maybe, but still, so far so good. Now consider the case in which light of wavelength in medium 1, lambda 1, is incident normally. For what values of D would light reflected from the two surfaces interfere constructively? Please ignore any phase changes that occur at the reflections. Right, so if we're normal, when we're going to want to have, right, will you get when you hit the boundary, okay, they're saying don't do a phase change at the boundary, but we get a speed change, a wavelength change, but not a frequency change. That's what happens when you refract these things. So we're going to be moving into this new area where we're moving 2D, and in that time 2D we want to go through multiples of wavelengths so that when it comes back out is back in phase. You know, if we've come in and we've hit, and I don't know, say at the boundary the reflected wave is at some particular phase, you know, it's maybe at the top of the oscillation, then but some of the wave has gone in and then back out again. We want it to come back out exactly in phase, being at the top of the oscillation again. So we need 2d, the distance in here, to be multiples of the wavelength, but the wavelength inside the medium, not the wavelength outside. So that's going to have to be lambda 2 that we've got there. So, but we need to get this in terms of lambda 1 and talk about how the wavelengths change. Now, we don't normally talk about wavelengths change quite as much on this, but it's quite easy to flip around, because you think we're talking about the change in the ratio of the what am I trying to say? The velocities is the velocity is the refractive index. So like n2 is going to be the speed of light divided by the velocity inside medium 2. You know, that is what refractive index is. So if we did that twice, then for n1 and n2, then we could say, well, n1 over n2, I mean, you might know all this already, is c over v1 multiplied by v2 over c. So we get that is v2 over v1, which again fits because you've got a slower velocity in n2, in this case in the n2 medium. So this is going to be less than 1 and this is going to be less than 1. So that's all great. Now we can also say with that, of course, that is the frequency. The velocity is the frequency times the wavelength for each one, and the frequency doesn't change when you go from one medium to the other. So they're going to cancel out. So the ratio of our refractive indices is the same as the ratio of the wavelengths, but inverted. So we've got then off of all of this that n1 lambda 1 is equal to n2 lambda 2 is what I'm getting to at the bottom of all of that, which means we can now get lambda 2 and say that it is n1 over m2 times lambda 1. So all of this just follows through from the fact that you know that the frequency hasn't changed and you know what the definition of refractive index is, which is this thing. It's a velocity ratio. Or at least that's one way of defining what refractive index is. So where have I got to on all of this? We've now got really sidetracked myself on everything. So we've got 2d is n lambda 2. Okay, I've used n. Well, I probably shouldn't have done because it might get confused with all these refractive indices. So we need d to be equal to, let's say, I over 2 lambda 2. And lambda 2 is all of that. So we're saying I over 2 n1 over n2 lambda 1, where for integer I. So this is where we've ended up. I'll write that out a bit clearer down the bottom just so you can see what I've ended up with. So d is equal to I over 2 n1 over n2 lambda 1 for integer I. So yeah, that was an interesting question for 9 marks. There was quite a lot of work to do there in all of that. But yeah, you need to make sure that you're using the right wavelength for all of these things when you change the medium. You know, there's no point looking at the distance d in terms of the wavelength in the other medium, in our n1 medium, because you would have moved the wrong distance. You wouldn't be back in phase again when you come out of that n2 material. So yeah, that's certainly taken us to the end of this video. We've got 3 questions left in the last one, but yeah, that took up quite a lot of time, that last one. So yeah, but yeah, nice set of questions. This has still gone quite nicely so far on this paper, but 1 video to go.